Right now, you're holding the result of an African tragedy in your hands. Inside your smartphone, laptop, gaming console are tiny components made from a metal mined in the jungles of Congo, where actual wars are fought over it. This is coltan, a dull black rock that looks like an ordinary riverstone but costs thousands of dollars per pound, and without which no modern electronics would work. Millions of people have been killed for this rock. Its extraction finances armed groups, destroys guerrilla reserves, and turns people into slaves. But without it, your phone wouldn't exist. Let's peer into the dark world of the most controversial mineral of the digital age, where every like and every post carries the price of a human life. First, the terminology. Coltan isn't an official mineral name. It's short for columbite tantalite. It's an ore containing two metals, niobium, which used to be called columbium, and tantalum. It's tantalum that makes coltan so valuable. It's a silvery gray metal with a unique combination of properties. It doesn't corrode at all, withstands extreme temperatures, has high capacitance, and barely conducts electricity because of a thin oxide film on its surface. That last property revolutionized electronics. Tantalum is used to make capacitors, components that store and discharge electrical charge. Tantalum capacitors are microscopic, the size of a grain of sand, but they have enormous capacitance. They're stable, reliable, work for years without degrading. Every smartphone contains 40 to 50 tantalum capacitors. A laptop, up to 100. Gaming consoles, cameras, even electric toothbrushes. Tantalum's everywhere. Coltan looks like black or dark gray rock with a metallic shine. Heavy, density around 8 grams per cubic centimeter, almost like lead. If you pick up coltan, you feel it's unusually heavy for its size. It occurs as coarse crystals or grainy masses in granite formations. Nothing special to look at, just a rock. But you can get anywhere from $100 to $400 per kilogram, depending on tantalum concentration. The main problem with coltan is geography. About 60% of the world's reserves are in one place. The eastern provinces of the Democratic Republic of Congo, especially Kivu and Ituri. This is one of the most dangerous regions on the planet. For decades, there's been a civil war involving dozens of armed groups that control the mines and use the profits to buy weapons. The story of the coltan rush began at the turn of the millennium. In the early 2000s, demand for tantalum exploded due to a boom in mobile phone and gaming console production. Sony released the PlayStation 2, Nokia and other manufacturers were churning out millions of phones. The price of coltan skyrocketed from $30 to nearly $400 per kilogram. A real gold rush started in Congo, only black. Tens of thousands of people dropped everything and headed into the jungle to dig for coltan. Armed groups seized control of the deposits. Murders, rapes, forced labor began. Kahuzi-Biega National Park, home to mountain gorillas, was overrun by miners. Animals were killed for meat, or simply because they got in the way. The gorilla population plummeted by 90% in just a few years. The UN published a report confirming that coltan sales were financing a conflict that had claimed millions of lives, the bloodiest war since World War II. Armed groups controlled the mines, forcing local populations to work for free or for pennies, smuggling coltan through Rwanda and Uganda, selling it to middlemen who shipped it to China and Europe for processing. Coltan extraction in Congo is mostly artisanal, meaning small scale, no machinery. Miners work in rivers and streams, washing ore in pans like gold prospectors. Coltan's heavier than regular sand and pebbles, so it settles at the bottom of the pan. Or they dig pits in the forest, sometimes 30 feet deep, with no reinforcement. Cave-ins kill people regularly, but nobody keeps track. The working conditions are horrific. People stand waist-deep in murky water all day long, washing tons of rock for just a few pounds of coltan. They make $1 to $5 a day, more than farming, but still poverty. No safety, no rights. Kids work right alongside adults. Women are forced into labor or worse. Coltan gets collected, dried, and sold to local traders. They haul it to regional centers where Chinese and other foreign companies have warehouses. There, they weigh the coltan, test the tantalum concentration with handheld analyzers, pay cash. Then they ship it out by plane or truck through neighboring countries, Rwanda, Uganda, Burundi, to mask where it came from. Rwanda officially exports hundreds of tons of coltan every year, even though it has almost no deposits on its territory. It's obvious what's happening. It's a transit point for Congolese coltan. The international community knows, but stopping the flow is hard. Borders in the region are porous. Corruption thrives. Tracing the origin of a specific shipment is nearly impossible. The coltan gets shipped to China, where most of the processing facilities are concentrated. There, it's melted in electric arc furnaces at temperatures exceeding 3,600 degrees Fahrenheit. What comes out is slag containing tantalum and niobium oxides. This slag gets treated with hydrofluoric acid, producing fluorides, which are then reduced to metals through complex chemical processes. Tantalum is incredibly refractory. Its melting point is around 3,000 degrees Celsius, third highest after tungsten and rhenium among all elements. That makes processing energy intensive and complex. Extracted tantalum is converted into powder, which is then pressed, sintered, and turned into anode foils for capacitors just a few micrometers thick. A tantalum capacitor works simply. Thin foil is coated with an even thinner film of tantalum oxide, which acts as the dielectric. Thanks to the microscopic thickness of this film and the massive surface area of the porous structure, you get enormous capacitance in a microscopic volume. This allows electronics to be compact. Without a tantalum capacitors, smartphones would be the size of bricks. Legal coltan mining exists. Australia, Brazil, Canada have deposits and extract coltan using industrial methods that comply with environmental and labor standards. But the cost is higher because you have to pay decent wages, maintain safety standards, and rehabilitate the land. Congolese coltan, extracted through what's essentially slave labor, is cheaper, so demand for it persists. There are also synthetic alternatives. Ceramic capacitors based on barium titanate can replace tantalum capacitors in some applications. They're cheaper and aren't linked to conflict. But for the most compact devices with high reliability requirements, tantalum remains irreplaceable. Military electronics, medical implants, aerospace equipment, they only use tantalum. Tantalum demand holds steady, around 2,000 tons a year. That doesn't sound like much compared to the millions of tons of copper or steel, but given its rarity and concentration in one region, even that amount creates enormous pressure. Every new smartphone, every data center, every 5G cell tower requires tantalum capacitors. Tantalum prices fluctuate between $150 and $300 per kilogram for the metal, or the equivalent for ore depending on concentration. For comparison, gold runs about $60,000 per kilogram. Tantalum's cheaper, but you need way more of it. And extraction is concentrated in a conflict zone, making it strategically critical. The environmental fallout is horrific too. The Congo jungle, one of the planet's largest tropical rainforests after the Amazon, is home to unique species. But artisanal mining is wrecking ecosystems. Forests get chopped down for mines and miner camps. Rivers become polluted with washed-out rock that kills fish and aquatic life. Poaching thrives. Miners hunt wild animals for food. There are attempts to recycle tantalum from electronic waste. Old cell phones, computers, devices contain tantalum capacitors. Technologies exist to extract and recycle them, but economically it's tough. You have to collect massive quantities of old devices, disassemble them, isolate tiny components, remelt everything. Right now, only 5 to 10% of tantalum comes from recycling. Some activists are calling for a boycott of electronics, or at least mindful consumption. Don't swap your smartphone every year. Repair instead of tossing it. Buy used. But here's the reality. Most people don't even know about coltan and the problems tied to it. Manufacturers don't advertise the dark side of their shiny gadgets. There's hope in technological progress. New types of capacitors are being developed that could eventually replace tantalum ones. Graphene supercapacitors promise even higher capacity in smaller sizes. But mass production is years, maybe decades, away. For now, tantalum remains a critical element of the digital age. The irony? Congo is one of the poorest countries in the world, despite its incredible wealth of natural resources. Cobalt, coltan, copper, gold, diamonds, all buried in Congo's soil. But corruption, conflict, and exploitation by foreign companies mean that wealth never reaches the people. It's a classic resource curse, when natural resources become not a blessing, but the cause of endless wars and suffering. The roof of SoFi Stadium in Los Angeles weighs 31,000 tons, which is roughly the same weight as the entire Eiffel Tower sitting on top of a football field. And somehow this massive structure stays suspended in the air, covering 70.2 acres without a single support column underneath. That roof is made entirely of steel beams, each one precisely engineered to carry thousands of tons of weight, while allowing the structure to flex and move with California's earthquakes and temperature changes. So how do you actually make steel strong enough and precise enough to build something this massive? Where does all that metal come from? And how does it go from raw iron ore to a beam that's holding up 31,000 tons of roof? Today, we're going inside the factory in Ohio, where every single one of those steel beams was made. And I'm going to walk you through the entire journey from the moment iron ore arrives at the plant to the moment a finished beam gets bolted into place 70 feet above the field in Inglewood, California. The factory is the Nucor Steel Mill in Marion, Ohio, which is a mid-sized industrial town about 40 miles north of Columbus. And when you pull up to this facility, you see a sprawling complex covering over 1,000 acres, where some of America's largest construction projects get their structural steel. What makes this particular plant special is that they specialize in something called wide flange beams, which are those massive W-shaped steel beams you see in skyscrapers and stadiums. And the entire SoFi Stadium project was manufactured right here at this one location. The raw materials start arriving by train several times a week, with deliveries of about 10,000 tons of iron ore coming from Minnesota's Mesabi Range, along with limestone from Michigan quarries, and metallurgical coke that's been processed from coal. All of these materials get stockpiled in massive outdoor yards, where you can see mountains of reddish-brown iron ore sitting next to gray limestone piles. And from here, everything gets moved on conveyor belts into the main building where the transformation begins. At the heart of the facility, there's a blast furnace that stands 12 stories tall. And even from the outside, you can feel waves of heat coming off the structure, because inside the temperature is running at 3,200 degrees Fahrenheit. The way it works is actually pretty straightforward. Iron ore, limestone, and coke get loaded into the top of the furnace, while superheated air gets blasted up from the bottom at speeds over 600 miles per hour, creating this incredibly intense chemical reaction. What's happening inside is that the extreme heat is literally ripping iron atoms away from the oxygen and other elements they're bonded to in the ore, and all the waste material rises to the top as liquid slag that gets poured off and ends up being used for cement production. The pure molten iron sinks to the bottom and collects in this glowing orange pool that you can see through special observation windows. And every few hours, they tap the furnace and the liquid iron flows out into these enormous ladles that each hold about 250 tons of metal. Those ladles get picked up by overhead cranes and moved about 60 feet over to the next building, where the iron gets converted into the specific type of steel needed for structural beams. In the steelmaking building, there's what's called a basic oxygen furnace. And this is where the chemistry gets really precise, because the difference between iron and structural steel comes down to exact percentages of carbon and other elements. They pour the molten iron from the blast furnace into this massive vessel, and then they blast pure oxygen into it at supersonic speeds, which ignites the carbon dissolved in the iron and creates these huge flames shooting 30 feet into the air. The entire process takes about 20 minutes, And during that time, they're constantly testing the composition and adding precise amounts of other elements like manganese and silicon to get exactly the right mix. For structural steel, like what's used in SoFi Stadium, they need the carbon content to be around 0.2%. If there's too much carbon, the steel becomes hard but brittle and could crack under stress. But if there's too little carbon, it becomes too soft and will deform under the weight of the structure. The margin for getting this right is incredibly tight, because one small mistake at this stage means the steel won't meet the structural requirements and can't be used for a project like SoFi, where lives depend on it. From the oxygen furnace, the molten steel flows into continuous casting machines, where it starts taking solid form, pouring into water-cooled molds that shape it into thick rectangular slabs called blooms that are about 10 inches thick and 3 feet wide. These blooms come out still glowing bright orange at around 2000 degrees Fahrenheit, and they immediately go into reheating furnaces where they're brought back up to exactly 2300 degrees before heading to the most important part of the whole process. The rolling mill is where these thick blooms of steel get transformed into the distinctive W-shaped beams that you see in construction, and when you watch this process, it's absolutely incredible. The glowing steel passes through a series of massive rollers, and each set of rollers has a different shape cut into it that progressively forms the W profile. In the first pass, the bloom gets compressed and starts elongating, and you can literally see the metal flowing like thick honey as these rollers that are applying thousands of tons of pressure reshape it. After about 12 passes through different roller sets, the distinctive W shape starts emerging. You've got the wide horizontal flanges on the top and bottom that provide strength against bending, and the vertical web in the middle that provides stability against twisting. For SoFi Stadium, they needed beams ranging from 14 inches deep for smaller supports all the way up to 44 inches deep for the main roof structure, and each size requires a completely different set of rollers. The precision required here is absolutely critical, because these beams need to be accurate to within 1/8 of an inch across lengths that can be up to 75 feet long. After the beams come out of the rolling mill, they're still around 1000 degrees Fahrenheit, so they go through a controlled cooling process where they're laid out on cooling beds and air-cooled down to room temperature over the course of several hours. Once they're cool, each beam goes to the fabrication area where they get cut to exact lengths using massive saws with carbide-tipped blades, and this is where the beams start being customized for their specific locations in the stadium. For a project like SoFi, every single beam has a unique set of holes that need to be drilled at precise locations for the bolts that will connect it to other beams. And these hole locations are programmed into computer-controlled drilling machines that can position a drill bit accurately within 1/16 of an inch. Some of the main roof beams have over 200 holes drilled into them, and each hole has to be exactly the right diameter and positioned exactly right, because when you're connecting beams that are holding up 31,000 tons, even a small misalignment creates dangerous stress concentrations. After fabrication, every single beam goes through the most rigorous inspection process you can imagine. And there's a very specific reason why this quality control is so incredibly strict. On July 17th, 1981, the Hyatt Regency Hotel in Kansas City had these suspended walkways in the atrium, and during a crowded party, one of the walkways suddenly collapsed onto the one below it, and both of them crashed to the floor. 114 people were killed, and over 200 were injured, and the investigation revealed something absolutely terrifying. The original design had called for the steel hanger rods to run continuously from the ceiling through both walkways, but during construction, someone made what seemed like a minor change. They used two separate rods, with the upper walkway hanging from the ceiling and the lower walkway hanging from the upper one. This seemingly small modification doubled the load on the connection points, and under the weight of the crowd, the connections failed catastrophically. That single decision to change how the steel components connected to each other became one of the deadliest structural failures in American history. That tragedy completely transformed structural steel quality control. Today, at the Nucor Marion plant, after fabrication, every beam goes through ultrasonic testing, where sound waves pass through the entire length of steel, detecting any internal flaws or cracks as small as 1/10 of an inch. They also do magnetic particle inspection on every connection point and weld to make sure there are no surface defects, and dimensional inspection with laser scanners to verify that every hole is in exactly the right place and every beam is exactly the right length. The rejection rate for structural steel destined for major projects is around 8%, which means roughly 1 out of every 12 beams that makes it through fabrication never leaves the plant because it doesn't meet specifications. After what happened at the Hyatt Regency, nobody in the structural steel industry is willing to take chances with quality control. The beams that pass inspection get loaded onto specialized rail cars for the journey to Los Angeles, and we're talking about a pretty massive logistics operation here. For the SoFi Stadium project, they shipped over 4,000 individual steel beams, weighing a total of 31,000 tons over the course of about 18 months, with trains leaving Marion several times a week. The route takes them west through Indiana and across the Great Plains, then through the Rocky Mountains and across the desert into Southern California, a journey that takes about 5 days. When the trains arrive at the rail yard in the City of Industry, just east of Los Angeles, the beams get transferred onto specialized trucks with extendable trailers because some of these beams are 75 feet long and weigh over 15 tons each. The trucks then have to navigate through LA traffic to get to the construction site in Inglewood, and for the largest beams, they can only move them at night when traffic is light, and they can get police escorts to manage the oversized loads. At the construction site, the real challenge begins because these beams need to be lifted into position and connected together 70 feet above the ground to form the roof structure, and the margin for error is essentially zero. The construction crews use massive mobile cranes that can lift up to 500 tons, and each beam has to be maneuvered into place so that all those pre-drilled holes line up perfectly with the holes in the beams it's connecting to. The connections use high-strength bolts that are torqued to very specific tensions, typically around 700 foot-pounds, and every single bolt gets checked multiple times because these connections are what's holding the entire 31,000-ton roof structure together. The roof design actually allows for up to 6 inches of movement in any direction to handle thermal expansion and seismic activity, which means the steel needs to be strong enough to carry the weight, but also flexible enough to move without cracking. When the Hyatt Regency walkways collapsed in 1981, structural steel was already a mature technology that had been used successfully for decades. But that disaster taught the industry that you can never assume anything about connections and quality. Today, 44 years later, SoFi Stadium stands as proof of how far the industry has come. 31,000 tons of steel suspended over 70 acres, engineered to survive earthquakes and support the weight while still allowing the structure to flex and move. You've now seen how iron ore gets transformed at 3,000 degrees into molten steel, how that steel gets rolled and shaped into precise W-beams, why 8% of production gets rejected before it ever leaves the factory, and how every connection point gets inspected multiple times because the lessons from past tragedies are built into every step of the process. If you found this interesting, subscribe to see more deep dives into how the massive structures around us actually get made. Thanks for watching. In every second of our lives, there are metals we don't even suspect. Without them, there would be no smartphones, electric cars, or even jet aircraft. And now imagine a place where, in the middle of the desert, under the scorching California sun, the United States creates a strategic resource of the future without a single pound of Chinese raw materials. Here, at Mountain Pass, they mine 43,000 tons of rare earth metals annually. Rocks that look ordinary are transformed into materials for lasers, engines, and defense systems. But there's something almost no one knows about. And if you watch till the end, you'll understand why this dust from the desert can change the world. Today here, in the dust and heat, MP Materials Company mines 43,000 tons of rare earth concentrate per year, all without a single pound of Chinese raw materials. For a country that for decades depended on imports from China, this is a strategic breakthrough. The main star of this place is basanite, a mineral that looks like an ordinary stone, but contains treasures inside: lanthanum, cerium, neodymium, and praseodymium. These very elements give life to modern magnets, lasers, electric cars, and jet aircraft. Everything begins in the depths of the quarry. Huge excavators and 300-ton trucks carry rock to the crusher. Next comes the flotation process, similar to a magic sieve. Crushed ore is mixed with water and special reagents. All this turns into foam, and bastnasite particles float to the surface, while waste settles to the bottom. After flotation, bastnasite goes for chemical expertise. In MP Materials laboratories, it's transformed into concentrate, and then into individual elements. This is a complex sequence of extractions and washes, where each metal chooses its own path. Once, this stage was performed in China. Now the United States is gradually building a full production cycle, from ore to finished magnets. Thanks to this, the country has already replaced 80% of its former imports from Asia, and this is just the beginning. It sounds like science fiction, but it's a fact. 2 pounds of cerium can become material for optical lenses of laser systems in military equipment. Other elements, like neodymium, are used in powerful magnets of jet engines and in missile guidance systems. All this means that every ton of ore from Mountain Pass isn't just raw material. It's a piece of American defense independence. The California desert isn't just scorched by the sun, it's politically charged. Mountain Pass is a symbol of a new era where technology and geopolitics merge. Today, American engineers, in hard hats and safety glasses, are literally building their own supply chain of the future, step by step displacing the Chinese monopoly. Just as in the 60s, when the United States first launched a satellite, now they're trying to be first to build an independent rare earth elements industry. And it all starts right here, among the sands, where it was once quiet, but now machines rumble, and the fire of smelting furnaces glows. If you gather all the rare earth elements mined here per year, it's 43,000 tons of concentrate. Outwardly ordinary dust, but actually strategic raw material, more valuable than gold. And if this dust were transformed into finished products, it would power more than 100,000 electric vehicles, those that race without a drop of gasoline thanks to neodymium magnets in motors. The same metals would ensure the operation of hundreds of guidance systems for F-35 fighters, where precision depends on microscopic lasers and sensors. And also, tens of thousands of medical lasers used for eye surgeries or to stop bleeding in military hospitals. The irony is that Mountain Pass isn't a megapolis or a Silicon Valley laboratory, but a patch of land in the middle of the desert. But it's precisely this place that's becoming a PowerPoint again. Every kilogram of cerium mined here is a potential lens for lasers in defense systems. Every gram of neodymium is a piece of an engine for an electric car or satellite. It's worth talking separately about cerium. Cerium isn't just another metal on the list of rare earth elements. It's one of those that sits quietly beneath the surface of technologies, but without it, the modern world would look completely different. Imagine a desert quarry, drilling rigs, machine cries, and dust. And among all this, under sand and stone, hides a complex chemical actor that transforms from an ordinary mineral into a material that affects aircraft, phones, and even medicine. In appearance, an ordinary grayish powder, nothing special. But this is a true alchemist among metals. Without it, there would be no clean glass in telescopes, no shine in smartphones, no precision of lasers, and no cleaner air from automobile exhausts. 1 gram of cerium can do what other materials can't even in hundreds of times larger quantities. Cerium is a true master of transformations. In catalysts, it behaves like a chemical chameleon. It intercepts and releases oxygen, converting harmful gases into harmless ones. In glass, it extinguishes ultraviolet light, makes lenses transparent as crystal. Its oxide polishes phone screens, cameras, optical devices, literally erasing microscopic scratches from surfaces to perfect smoothness. Among workers at the plant, there's a joke. Without cerium, the world wouldn't shine. And there's truth in this. Because when it gets into engineers' hands, everything around starts to shine. Literally. It helps see farther, move faster, burn cleaner, heal more precisely. All this from desert dust, from a place where heat reaches 110 degrees Fahrenheit and wind sweeps away traces in a few minutes, as a symbol that even in the driest desert, the future can be born. Mountain Pass was once just a point on the map, the only mine of this type in all of North America. But now it's surrounded by an entire network of structures that transform crude ore into pure elements, ready for the most complex technologies, from electric motors to jet guidance systems. MP Materials Company has built here not just a mine, but a closed-cycle production, something America lost back in the 1990s when all supplies depended on China. After many years of research and investments in hundreds of millions of dollars, new lines operate almost without human participation. All processes are controlled by computers. Sensors measure compound purity, robotic cranes move containers, and special cameras capture every dust particle. Air in laboratories is so sterile that it feels like it's not a desert, but a space station. Everything that comes out of these shops is sent to other factories, which are also being built inside the country. In Texas and Ohio, they're building factories that will manufacture permanent magnets, precisely those that ensure the operation of Tesla electric motors, wind turbines, or fighter guidance systems. Once these magnets were supplied from China almost 100%, but now America plans to completely switch to its own materials by 2030. People who work here say they feel part of something bigger than just production. When they watch as a substance comes out of desert soil that will later turn into part of a satellite or a high-precision laser, it resembles a true miracle. Next to the quarry grow warehouses, laboratories, transport hubs, and on the horizon, also solar panels that power this giant. After the mine closed in 2002, when Chinese companies effectively monopolized the rare earth elements market, only a few dozen workers remained in the Mountain Pass area, maintaining security and basic infrastructure. The nearby settlement declined. Stores closed, roads overgrew with weeds, and local families moved out to look for work. When in 2017, MP Materials Company bought out the assets and launched a modernization program, the situation began to change literally from scratch. Over several years, more than 800 jobs were created at the enterprise itself, not counting hundreds of related ones, in transport, chemical supply, technical service, energy, and even local services. In neighboring towns, cafes reopened, schools received funding, and roads, repairs. Besides direct vacancies, MP Materials launched a professional training program, cooperating with local colleges. Graduates of technical specialties can now do internships right at the modern processing plant, where they learn to work with automated lines, flotators, hydrocyclones, and chemical separation systems. Interestingly, jobs here are very diverse, from geologists, chemical engineers, process operators, to programmers and data analysts who control plant operations through digital panels. Each shift means tens of thousands of parameters read by sensors in real time. In a broader sense, the revival of Mountain Pass has become a symbol of the return of American manufacturing, which for decades was exported abroad. Against the background of political statements about reshoring and strengthening the internal supply chain, this project is often cited as proof that even in the desert, you can create a modern, profitable, and stable industry. Every year, over 1 billion feet of steel chains are produced worldwide, from those that lift sea cranes to those that support bridges. But only a few of them go through a journey where precision is measured in microns, and every spark during welding is the beat of a metal heart. Imagine, a piece of ordinary steel transforms into a link capable of withstanding tens of tons. How exactly? In a few minutes, you will see how a force that cannot be broken is born. And if you watch until the end, you'll learn the secret that determines whether a chain will survive under maximum load. Our journey begins not in the noisy workshops, but much earlier, in the design office. It is here, at the design stage, that engineers determine what our chain will be like. What is it intended for? What loads must it withstand? Will it operate in an aggressive environment? The answers to these questions dictate the choice of material. In the vast majority of cases, for the manufacture of welded chains used in lifting mechanisms, industry, construction, or as fastening elements, we use high-quality steel rod. Take a look at these warehouses. Here they are, our round bars, thick, heavy, shining with strength. They can have different diameters, from a few millimeters for light chains to tens of centimeters for true giants that lift tons of cargo. Each batch of rods undergoes a thorough incoming inspection. The metallurgical laboratory checks the chemical composition of the steel, its mechanical properties, tensile strength, impact toughness. This is critically important, as the safety and reliability of the final product depend on the quality of the raw material. Only rods that meet the highest standards are allowed for further processing. This is the first, but extremely important, step in ensuring the unsurpassed quality of our chains. So, our selected steel rod is ready for transformation. The next stage is cutting. Here, high-precision cutting machines come into play, which, like surgeons, cut long rods into sections of a perfectly specified length. These sections will become our future links. Every millimeter matters, as the uniformity and correct geometry of the entire chain depend on the cutting accuracy. Operators carefully monitor the process, controlling the dimensions of each blank. And now we move on to one of the most spectacular stages: forming the link. Look at this powerful machine. It's an automatic press or a special bending unit. The metal section, heated to a plastic state, and sometimes without preheating if the diameter and steel grade allow, is fed inside, and under colossal pressure or a complex bending motion, it is transformed. Before our eyes, a straight rod is bent into a perfect oval or round shape, the future link. It is important that the ends of the rod are not completely joined, leaving a small gap, a seam. This seam will be a key element for the next stage. The newly formed link is fed to a mechanism that threads it through an existing link of the chain. It's like an amazing dance where one part is woven into another, creating a single whole. And now, the most important moment: welding. Most often, electric resistance welding, or flash butt welding, is used for chains. This is a high-tech process where the ends of the link that form the seam are clamped between electrodes. A powerful electric current is passed through them, which instantly heats the metal to its melting point. See those bright flashes? The fountains of sparks? That's the metal melting. And then under the pressure of the electrodes, an upset occurs. The ends are joined, forming a strong, homogeneous weld. In some cases, especially for very large chains, arc welding may be used, but the principle remains the same, creating an unbreakable metal joint. This weld is not just a connection. It's the weakest point of the link, and it is here that its future strength is established. Welding masters are true virtuosos, as the integrity of the entire chain depends on their work. After welding, the excess metal can be trimmed or processed for smoothness. The newly formed and welded chain, although strong, has not yet revealed its full potential. To meet the highest requirements for strength, durability, and safety, it goes through a series of finishing processes. The first of these is calibration. The long chain passes through special dies under pressure. This ensures the precise dimensions of each link, eliminates minor deformations after welding, and gives the chain uniformity. A calibrated chain will be ideal for working with sprockets and other mechanisms where precision is critical. After calibration, the chain heads to the heart of the factory: heat treatment. This stage is one of the most important and determines the final mechanical properties of the chain. Depending on the steel grade and desired characteristics, the chain may undergo several operations. Let's talk about each of them separately. Quenching. The chain is heated to a high temperature in special furnaces and then rapidly cooled in water, oil, or a polymer solution. This makes the steel very hard but brittle. Tempering. To eliminate the brittleness after quenching and increase the ability to absorb impact energy without breaking, the chain is heated again, but to a lower temperature and cooled slowly. This process gives the chain the necessary balance between hardness and ductility, normalizing. Sometimes, instead of, or in addition to, quenching and tempering, normalizing is used, heating to a certain temperature, followed by cooling in air. This improves the metal's structure and relieves internal stresses. All these processes are carefully controlled by computer systems, as even a small change in temperature or holding time can significantly affect the final result. Heat treatment is a true art of controlling the properties of metal. After heat treatment, the chain comes out of the furnace, but its journey is not yet over. At this stage, it may have scale on it, a layer of oxides formed at high temperatures. Therefore, the next step is cleaning. This usually happens in special shot blasting chambers. Thousands of small metal shot particles under high pressure bombard the surface of the chain, knocking off scale and other contaminants. The result? The chain becomes clean, smooth, with a pleasant metallic sheen, ready for the next stages. In order for our chain to serve long and reliably even in difficult conditions, it needs protection from corrosion. This is where coating comes into play. The most common method is galvanizing, which can be hot dip or electroplating. In hot dip galvanizing, the chain is immersed in a bath of molten zinc at a temperature of 860 degrees Fahrenheit. Zinc, interacting with steel, forms a strong protective coating that not only prevents rust, but also has the property of self-healing for minor damages. In electroplating, the chain is placed in an electrolytic solution, and under the action of an electric current, zinc deposits on the surface of the steel. This coating is thinner, but gives the chain a more aesthetic appearance. In addition to galvanizing, other types of coatings may be used. For example, polymer paints, or special anti-corrosion compounds, depending on the purpose of the chain. We are approaching the final stage, and this is perhaps the most responsible moment: testing. It is here that our chain confirms its readiness to perform the most complex tasks. Every single chain undergoes a whole complex of checks for compliance with international safety and quality standards. Look at this huge test stand. Here the chain is subjected to colossal loads. It is stretched with a great force, which significantly exceeds its nominal working load, but at the same time does not reach the breaking point. This is the so-called proof load test. During this process, possible hidden defects and weak points that could manifest during operation are revealed. If the chain successfully passes this test, it means that it will withstand the declared loads and ensure safe operation. In addition to this, other types of control are carried out. Specialists carefully inspect each link for cracks, deformations, quality of welds, and coating. With the help of special calipers and measuring instruments, the compliance of the link sizes, their shape, and the chain pitch with the specified parameters is checked. From each batch of chains, samples are taken, which are then subjected to breaking tests. This allows to determine the maximum breaking force that the chain can withstand and to make sure that it meets or exceeds the established norms. These are brutal but necessary tests that guarantee that the entire batch of products is reliable. Only chains that have successfully passed all stages of quality control without exception are given the right to leave the factory premises. Each batch is accompanied by a certificate of conformity, which confirms its characteristics and the passing of all tests. This is our guarantee, a guarantee that you are getting a product of the highest quality and reliability. And now, dear viewers, we see the final result. Chains of different sizes, diameters, with different coatings, neatly laid in coils, ready to be sent to all corners of the world. They will go to the construction of skyscrapers, to port cranes, to ships, to agriculture, to production lines, everywhere where unbreakable strength, reliability, and safety are needed. From small, elegant chains for decorative purposes, to huge ones that lift bridges, each of them has gone through a long and complex path of transformation, from raw metal to a high-tech product. Imagine a toxic gas that was once used as a weapon in war. Today, however, your plastic windows, the medicines in the pharmacy, or even your drinking water wouldn't exist without it. The United States produces over 12 million tons of chlorine each year, a capacity that could turn the ocean into a giant swimming pool in a matter of days. But the real mystery is something else. only a tiny fraction of this volume is used for disinfection. So where does the rest go? Watch until the end, and you will learn a secret that will turn your idea of this gas upside down. The United States is one of the world's largest producers of chlorine. Annually, the country's factories produce over 12 million tons of this gas. This number is simply mind-boggling. Imagine the weight of the aircraft carrier Gerald R. Ford, the heaviest warship in the world. It's about 100,000 tons. This means that in a year, American industry produces as much chlorine as 120 such aircraft carriers weigh. This huge amount makes chlorine one of the 10 most produced chemicals in the country. It all begins not in a laboratory, but deep underground. The main ingredient for our recipe is ordinary rock salt, or sodium chloride. But it's not brought to the factory in salt shakers. It is either mined in the form of huge blocks, or, much more efficiently, pumped out from under the ground. Water is pumped into deep underground salt deposits. The water dissolves the salt, forming a saturated salt solution called brine. And it is this concentrated, salty as tears solution that is our raw material. But it's still dirty. It's full of impurities, calcium, magnesium, and other minerals that can clog our expensive equipment. So before the main show begins, the brine undergoes a thorough cleaning. It is passed through a whole series of tanks where, with the help of chemicals, all impurities are precipitated and filtered out of it. At the exit, we get a perfectly clean, transparent, and very salty solution, ready for the main event, electrolysis. Now let's move to the heart of the factory, to the so-called cell room. This is a huge, noisy hall, filled with rows of strange closed tanks, connected by a network of pipes and thick electrical cables. These are electrolyzers, or cells. It is here that all the magic, or rather, all the chemistry, will take place. Let's imagine one such electrolyzer. Essentially, it's a box into which our clean salt solution is poured, and two electrodes are immersed in this solution, a positively charged anode and a negatively charged cathode. And now, a direct electric current of colossal strength is applied to these electrodes. And here the breakdown begins. The salt molecule in the water breaks down into positively charged sodium ions and negatively charged chloride ions, and the electric field forces them to move. The positive sodium ions are attracted to the negative cathode like a magnet, and the negative chloride ions to the positive anode. And here, at the anode, what it was all for begins. Each chloride ion that has stuck to the anode gives up its extra electron. Two such chlorine atoms, having lost their charge, immediately unite, forming a molecule of gaseous chlorine. Billions of these molecules gather together, and tiny bubbles of a greenish-yellow gas begin to appear on the surface of the anode. This is our chlorine. The main resource for chlorine production is electricity. The chlor-alkali industry is one of the largest consumers of electricity in the entire US manufacturing sector. To produce 1 ton of chlorine, approximately 2,500 kilowatt hours of electricity are needed. And now let's multiply this by 12 million tons per year. It turns out that this industry consumes about 30 billion kilowatt hours annually. This is more than the annual electricity consumption of entire states, like Vermont or Wyoming. This is a city of 1 million people, working all year just to break salt molecules. But what happens at the cathode? The sodium ions have arrived there. But they do not turn into metallic sodium. Instead, the electric current splits the water molecules in the solution into hydrogen and hydroxide ions. Bubbles of pure hydrogen are released at the cathode. This is our first byproduct. And the hydroxide ions remaining in the solution combine with our sodium ions, forming caustic soda. This is our second, incredibly valuable byproduct. But here, a huge problem arises. We have just obtained 3 substances: chlorine, hydrogen, and caustic soda. And they must never be mixed. Chlorine and hydrogen together form an explosive mixture, and chlorine and caustic soda react to form bleach, which we don't need at all. Therefore, the whole genius of the technology lies in separating these three products at the moment of their birth. For this, special membranes or diaphragms are used. Imagine that between the anode and the cathode, there is a thin, paper-like, but very clever partition. This membrane, made of a special polymer, is like a face control at a nightclub. It lets the positive sodium ions pass through to the cathode, but blocks the negative chloride ions, not letting them into the cathode space. Thus, chlorine is born and collected in one part of the cell, and hydrogen and caustic soda in the other. Now we need to collect our harvest. From the anode chamber, a wet, hot, greenish-yellow gas is continuously pumped out. First, it needs to be cooled. It is passed through heat exchangers, where it gives up its heat. Then, it needs to be dried. Chlorine is incredibly aggressive, especially when wet. It corrodes almost everything. But there is one substance it doesn't touch: concentrated sulfuric acid. So the wet chlorine is passed through towers, where it bubbles through sulfuric acid, which, like a sponge, absorbs all the water from it. The resulting dry, cold, but still gaseous chlorine is ready for the next stage: liquefaction. It is compressed under huge pressure and simultaneously cooled. Under this double blow, the gas turns into a transparent, amber-yellow liquid, similar to oil. This liquid chlorine is much more convenient to transport and store. It is poured into special thick-walled steel tanks or railway cars. Every step of this process takes place in conditions of absolute hermeticity, because a leak of this gas is deadly. And what about our byproducts? They are no less important. The hydrogen we obtained is collected, purified, and used either as fuel for the plant itself or sold for the production of ammonia or in the food industry. And the resulting caustic soda solution is pumped out, concentrated by evaporating the excess water, and sold. This is one of the most important products in the chemical industry, used for the production of soap, paper, aluminum, and much more. And so, from simple salt water, by passing a huge amount of electricity through it, people have learned to obtain three extremely important substances at once, which are the foundation for thousands of other products that surround us in everyday life. And now, let's see where all this huge amount of chlorine goes. You might think it all goes to disinfecting swimming pools, but that's just a drop in the ocean. In fact, less than 5% of all chlorine is used for water disinfection. So, where does the other 95% go? It is a key building block for other products. About 40% of all chlorine goes to the production of this universal plastic. The vinyl windows in your house, water pipes, medical IVs, vinyl records, the credit card in your wallet, all of this was born thanks to chlorine. Another 40% is used to create thousands of other organic and inorganic compounds: pharmaceuticals, solvents, refrigerants, herbicides, insecticides. The list is endless. And chlorine is also a key component for bleaching paper, giving it that same pure white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we get about 1,100 tons of caustic soda. This means that annually, American industry produces over 13 million tons of this important alkali. This makes chlor-alkali production a perfectly balanced business. When the demand for one product falls, the demand for the other may rise, allowing the plants to operate stably. So these millions of tons are not just statistics. They are proof that this sharp, suffocating gas is the invisible foundation for a huge part of the American economy, from the plastic pipes under our streets to the medicines in our pharmacies. Every year, new icebreakers are launched around the world, giants capable of cutting through ice several meters thick. These are ships whose mass can exceed 20,000 tons, more than the weight of an entire stadium filled with people. But how is this steel beast born from 1,000 metal blocks? What does the moment look like when a multi-story crane, with millimeter precision, installs a piece of the hull weighing hundreds of tons? And what happens when the ship's bow first cuts into an ice field, and the hull shudders from an impact similar to an earthquake? In this video, you will learn what is not shown to the public, from digital ghosts in design bureaus to the moment of truth when an icebreaker meets its first ice. Watch until the end, because a secret that few know awaits you. It all begins not with the roar of hammers, but with the silence of a design bureau. Before a single piece of metal is cut, thousands of engineers spend years at computers. They create a detailed three-dimensional model of the future vessel. This is a digital twin, where every screw, every weld seam, every meter of pipe is calculated. Using powerful computers, they simulate the most extreme situations. How the hull will interact with ice of different thicknesses. How the ship will behave in a hurricane. How it will withstand a collision with a multi-ton hummock. These are virtual crash tests, where the cost of an error is only processor time, not human lives. Only when every aspect of this digital ghost is perfected are the drawings sent to the workshop. Icebreakers are not built whole, like a model ship in a bottle. They are assembled from giant blocks, like a colossal Lego set. In huge workshops, the size of several football fields, the cutting of steel begins. For icebreakers, special low-temperature, high-strength alloys are used. Ordinary steel in the Arctic cold becomes brittle as glass and can crack from a strong impact. But this one retains its ductility and strength even at a temperature of -60 degrees Fahrenheit. The sheets of this steel can be incredibly thick. If a regular ship has a hull thickness of less than an inch, then an icebreaker in the so-called ice belt, the area that contacts the ice, can have a thickness of 2 inches or more. This is thicker than a bank vault door. Plasma cutters, controlled by a computer, with a hiss and showers of sparks, cut thousands of parts of the future hull from these sheets. Then these parts are welded into sections, and the sections into huge multi-story blocks. Each such block is already a finished part of the ship, for example, a piece of the engine room, or several cabins, already with part of the pipes and fasteners. Every weld seam here is a matter of life and death, so it is checked with X-rays and ultrasound to ensure the absence of the slightest defects. A symbolic moment arrives, the laying of the keel. On a huge construction site called a slipway or a dry dock, the first central block is installed. This is the spine of the future giant, and to this spine, like ribs to a spine, other blocks begin to be attached. Giant gantry cranes, looming over the entire dock, come into play. With incredible precision, they lift these multi-ton pieces, weighing hundreds of tons each, carry them through the air, and with millimeter precision, set them in place. Welders, resembling astronauts in their protective suits, connect these blocks into a single, monolithic hull. Gradually, day by day, a giant steel beast grows from these separate pieces, and its shape is its main weapon. The bow of an icebreaker is not sharp, like a regular ship's. It has a special, spoon-like shape. It doesn't cut the ice. It crawls onto it, and then, under the action of the colossal weight of the entire vessel, and this can be from 15 to 20,000 tons, it simply breaks the ice, like a person stepping on thin ice on a puddle. Its bottom is rounded, without a protruding keel, so that after breaking the ice, it can easily push the fragments aside and not get stuck. While the hull is growing, the heart is installed inside, the power plant. An icebreaker needs not so much speed as colossal, unstoppable power and torque. Therefore, most modern icebreakers are diesel-electric. Imagine that a whole power station is inside it. Several giant diesel engines, each the size of a bus, turn generators, producing megawatts of electricity. This energy is then supplied to huge electric motors, located in the aft part of the vessel, which directly turn the propellers. This scheme allows for maximum power on the propellers instantly and very precise regulation. The total power of the power plant can reach 50,000 horsepower, enough to power a small city. The propellers of an icebreaker are also a work of art. They are made of super strong stainless steel, have a huge diameter, and thick blades like the wings of an airplane, capable of withstanding impacts from ice flows weighing tons. When the hull is assembled and the main equipment is installed, the moment of birth arrives, the launch. If the ship was built in a dry dock, the dock is simply slowly filled with water, and the giant ship smoothly floats off its supports. If it was built on an inclined slipway, it is much more dramatic. The supports are cut, and the multi-thousand-ton machine, gaining speed, slides into the water with a creak and a roar, raising a huge wave. And so, this giant for the first time sways on the waves. But it is still far from ready. It is just an empty steel box with engines. It is towed to a fitting-out quay, and here the most complex part begins: the outfitting. Hundreds of miles of electrical cables, thousands of meters of pipes for water, fuel, sewage, ventilation are laid throughout the ship, forming its circulatory and nervous systems. Living modules, wardrooms, a galley, a medical unit are installed. Navigational equipment is mounted on the captain's bridge. Radars, sonars, satellite systems, powerful deck cranes, scientific equipment, a helicopter pad are installed. The entire ship is covered with a thick layer of thermal insulation. And then the time for the final exam comes. The icebreaker goes out into the open sea, away from the shore. On board, not only the crew, but a whole army of engineers, representatives of the shipyard, classification societies, and the customer. Each of them with their own notebook and a list of hundreds of items that need to be checked. It all starts with the basics. Full ahead. The command sounds from the bridge. The engine room comes to life, the diesel generators go to full power, and the giant propellers begin to accelerate the multi-thousand-ton machine. Engineers with sensors check everything: hull vibration, engine temperature, pressure in the fuel systems. The vessel accelerates to its maximum speed on clear water, which is usually not very impressive, about 17 knots. Then the command, "Stop engine." And everyone watches how many miles this giant will need to come to a complete stop. This is called the inertial coasting. Next, maneuverability. Hard to port. And the rudder is turned to the maximum angle. Everyone watches how large the turning circle will be. That is, how wide a circle the icebreaker will describe at a full turn. They test reverse, reaction speed to commands, the work of the autopilot. Every system, from the large engines to the small pump in the toilet, is turned on and off, checked under maximum load. They even conduct a so-called blackout test. They deliberately turn off the main power to check how quickly the emergency diesel generators will start and restore the operation of vital systems. Only when every item on the long list is checked off. But all this was just a warm-up. The real exam is ahead. Winter comes, and our icebreaker, fueled to the brim, heads north, towards its true calling: the first encounter with the ice. This is the moment of truth. The captain directs the vessel straight into an ice field. From the bridge, you can see the horizon turning into an endless white desert. First comes young, thin ice. The icebreaker passes through it like a knife through butter, with a light rustle and crackle. But then the ice gets thicker. And so, the vessel at full speed crashes into real, multi-year ice several feet thick. A deafening blow sounds, shaking the entire hull. This is not like a collision. It's like the sound of an earthquake. The whole ship vibrates, dishes in the cupboards rattle. The specially designed bow crawls onto the ice, and under the weight of thousands of tons of steel, it breaks with a loud crack, spreading giant cracks. The fragments, the size of cars, scrape against the sides with a grinding sound. And so, meter by meter, the icebreaker makes its way. Special sensors, installed throughout the hull, record the pressure that the ice exerts on the hull and transmit the data to the engineers. They check whether the real loads correspond to those calculated in the computer models. It returns to port for final adjustments.